In this particular lesson, we are going to learn about the different system models found within distributed systems. Actually, we are also going to expand our understanding and learn about the architecture or the building blocks of our distributed systems. So if you want to understand more about the various system models are found within the distributed systems, then this particular lesson is the right one for you. So hang on until the end of this particular video so that you learn more about the various system models. All right, thanks.
Distributed systems architecture and models. So we have two things here that we need to understand: the architecture of distributed systems and also the models, right? Now, architecture is a blueprint or how these particular systems are designed, and to help us achieve the correct design of our distributed systems, we need to have the different categories of models, as we are going to see. But first, we are going to introduce, maybe to understand the general organization and architecture of distributed systems, right? So we have the hardware component of these distributed systems, and of course we also have the software component, which maybe when we combine together will help us understand the overall architecture of a distributed system. So I'm not going to go into details of what hardware and softwares are, but we are just going to understand what are the various hardwares and softwares that are essential when crafting up a particular architecture of a distributed system. So our distributed systems are made or they actually have organization of multiprocessors. Yeah, since we have distributed systems and the nature of work that they perform, they need multiple processors. So that's kind of some kind of sub characteristic of a distributed system. They also have or operate under multiple computers. We are going to look at also the network heterogeneity, right? So when we have the architecture of distributed system, we can talk about multi-computer networks and computers. Most importantly is combining the two approaches: multiple computers running on multiple processors, right? So this brings in the idea of sharing memories, yeah, sharing the different components or objects, as you're going to say. So this can be achieved through bus connection or switch connection, as shown. So we have shared memory and private memory. I think the concept is very clear here. When you have multi-processors being maybe integrated within this multi-computer approach, this we have the two categories, shared and private memory. Yeah. So the concept is, within the private memory, as the name suggests, every processor, yeah, has or can holistically use their memory without sharing, right? So they have two options. As you can see, there's a bus approach where they can privately or connect the multiple processors, but the idea is each and every processor shares or don't share, but actually has their own memory. Of course, you have the switched option for the private memories, as you can see. Now, this is a concept whereby different computers or machine can always kind of substitute or give a particular processor an option to share this particular memory without really sharing those particular memory. When we talk about share memory or shared memory, as you can see, the bus approach, all the computers or the processors can be able to use the available memory. And also you can see there's a kind of a star topology under the switched network or switched option that allows the various processors to share that particular memory. So when you talk about this kind of architecture that is being implemented within the multiprocessor and multi-computer environment, we talk about sharing of memory. Now, this is a very important concept that is going to help us understand how the communication happens when we are going to look at group communication. And I think one of the vital components is this kind of sharing of memory. In a particular distributed system architecture, also we need to understand that there are multiple components that are actually brought together to operate as a single unit. Yeah, so we have multiple processors, as you have seen. Yeah, this aspect of bringing different hardwares and softwares, yeah, and bring them together to work together, that is what we refer to as heterogeneity. Yeah, so there are two terms here that we are going to look at: heterogeneity and homogeneity. Heterogeneity is actually integrating different technologies, so that they work together, right? So we can also have wireless connection within a particular distributed system, various, what we refer to as ubiquitous kind of computing. We also have high latency connections. These are issues also that we need to check, like latency. We also have wide area networks. I was actually talking about node heterogeneity. So we have mobile computers, different categories of computers that work within a distributed system. We also have high-end computers, we have networks, even users, yeah, can form this aspect of heterogeneity, because we can't really have distributed systems operating on their own. So we need to have users using these particular systems. Remember, we have categories of users that we're not going to actually list here, but we have those who are naive users, those who are expert users, developers, programmers, and so on. And the other wing is the network heterogeneity. In a distributed system, actually distributed systems are implemented on a network, right? So we can have this kind of implementation in different networks running different speeds. Like we have local area networks, we have wireless connections, we have wide area networks, and so on. So this concept of bringing on board different categories of networks so that we can have distributed system working is what we refer to as network heterogeneity. And this also forms the other aspect of architecture that we need to understand. Away from the hardware, we have software. And we are just going to keenly look at the three categories of software. Yeah, distributed operating system. Yeah, that means a distributed system must have a distributed operating system. We're going to see how then how it works. We also have network operating system. Yeah, any given distributed system must actually work under given network, and the operating system that's going to provide the essential services is actually the network operating system. So we have different categories of a network operating system, which I believe you can identify. The game changer in the distributed system is the middleware. Yeah, middleware actually is this kind of application that brings some kind of abstraction layer or installation layer that ensures that the different layers, or actually the different components within a distributed system, really don't need to know what the other component does. So it kind of brings in the abstraction component. So in a nutshell, we have different categories of operating systems. Yeah, like the DOS, that is the distributed operating system, runs within the shared memory. You remember I said that this sharing of memory will actually come up. So when you have tightly coupled OS, that means these kind of computers run under shared memory. We talk about multiprocessors. Yeah, so the fact here is we can have different computers running the same operating system, running under the same hardware features, and so on. That is what we refer to as homogeneous, right? So the main goal here is to manage. I think the key feature of any operating system is to manage and control how hardware resources are functioning. The other operating system, as I mentioned, is the network operating system. This one operates under loosely coupled, or what we refer to as a distributed memory, right? Loosely coupled operating system actually operates based on shared, or I mean distributed memory. Now, when we talk about distributed memory, we have the concept of heterogeneous. So heterogeneous, as you have seen, this kind of network operating system can work under different hardwares or even networks. So the main goal here is to ensure that local services and even the kind of requests from the client computers are actually accorded. Of course, we have the middleware, as I've mentioned. It brings some kind of added layer, right, that ensures that the different hardware and softwares work uniformly without really bothering to understand the kind of hardware or software that has been installed. Now, what are some of the characteristics of DOS, or distributed operating system? Yeah, so one thing that we have seen with DOS is that it operates within the environment of homogeneous, where we can have different machines running on the same operating system and also are actually implemented within the same hardware environment. So that is, the operating system should be in a position, it should not really bother to know what other computers is all about. We have OS that operate under different computers that are the same. I think I've already mentioned that. And I think also transparency factor. Remember some of the characteristics of distributed system. We talk about transparency. And that part of the distributed system that brings about transparency is the distributed operating system. So it doesn't really matter. The concept is the same, homogeneous kind of approach, where we have different machines running the same operating system and actually are implemented within the same hardware. Characteristics of network operating system, I've already mentioned. Yeah. Now, here, ideally, computers work in isolation, but the good thing is that we have the distributed application mechanism, right? So we have different services that are provided under different computers based on the network operating systems, right? So here, each computer has its own operating system with the network facility. I think I'll spare a lot of explanation. Just look at the normal organization, how network is implemented. We have client and server computers, or server computers actually running the network operating system, and how they are able to do what? To share resources. Yeah? So here computers tend to work independently, providing different services to the various clients. So here network operating system, I believe we understand how it works. The other application is the middleware. I've already mentioned the abstraction component. Yeah, so here it also provides some kind of transparency. Yeah, so that when other different hardwares or operating systems are actually connected, they don't really bother to understand what other or how the other kind of hardware operates. Like hardwares could be from different manufacturers, operating systems also could be different. We could have Linux, we could have Windows, and so on. So the main purpose of the middleware is to ensure that all the applications that are running within these different operating systems actually don't need to understand the kind of hardware or software that have been implemented, and that's what we refer to as transparency, or better still, offering openness to this kind of connected system. So I think these three applications, or rather operating systems, help us understand the kind of architecture that this particular distributed systems operate or under or in. So why should we have, or what is the need of actually middleware? Because as I'd mentioned, this is a very vital application or operating system for that matter. There was a desire, to actually ensure that various applications work seamlessly, right? So we had different network applications that were very hard to integrate or rather configure. So that is what motivated maybe the programmers to come up with this kind of application, the middleware. So also different departments or organization were running different operating systems, such as network operating systems from Linux and so on. So they wanted a very a single uniform interface that the other applications could actually understand. And I think the same concept is replicated. Yeah, we are going to look at distributed database distributed systems, how database distributed systems are implemented. So also it helps combine different databases running under different database management system. You could have Oracle, MySQL, right? So it also helps bring or combine all these to provide a single view of operation. Also transactions in different databases, right? Anything that actually is isolated, this middleware tends to bring and ensure that they talk together. So we can go ahead and give as many examples why we need a middleware as possible. All right, now with that understanding, the architecture of a distributed system actually is composed with different components, as you have already seen, right? Now different components comprise of different objects, yeah, and these objects within different components in a given distributed system needs to talk to each other. Now that particular point where a particular component needs to talk to a particular component by sending or actually invoking an object is what we refer to as interfaces within a distributed system. So I'll give an example is we can say a client computer talking to a server computer. Yeah, so it could be it could happen that a client computer is requesting for a particular service. Yeah, so we should have some kind of option to provide that particular service, and that is what we refer to as service interface. So the major known interfaces are the remote interface. We are going to see how the invocation happens, yeah, like having remote procedural call. So we need to have an interface where the two server and actually the client also allows the object call to happen. Of course, we have the object interfaces. Yeah, we can't really talk about object-oriented kind of programming without understanding how the programmer can program the different parts of the distributed system. So we have the object interfaces, or what we normally refer to as the application, yeah, programming interfaces that allows some set of methods to be called, arguments and so on. So if you are a good programmer and you want to maybe ensure that you have the right interface to interrogate the distributed system, then we need to have the object interfaces. So they're very, very crucial when you talk about the architecture of this particular distributed system. Now, to wrap up the entire architecture, we have two major I can talk about the two major system architectures. That is the client server. I think I've already mentioned about that, and since I said that we need to have some kind of understanding of how a network operates, or how we bring on board the different clients and server computers in a network, if you understand that concept, then that's how the distributed system architecture looks like. We can give examples. Yeah, we have different servers: file server, print server, web server. All of them communicate in a similar manner. It's only that the resources that is requested is a bit different. But we are going to look at maybe other aspects of this kind of architecture. We're going to break them down to understand them in detail, right? We talk about the system models. Yeah, so we're going to look at this kind of system architectures with respect to the specific part of the architecture. So we are going to look at the physical model, talk about the fundamental models, and so on. So we can give examples, but what we need to understand in this kind of architecture is that we have one process actually requesting for some kind of service, which is actually that can be provided by a given server. As you know, server is a dedicated computer within a network. So it goes round and round, be it print server, be it web server, be it any kind of server and client machine. We can always have that kind of arrangement. All right, sorry, I was still looking for something. Now, here is a diagram. Here's a diagram that shows how this kind of two components or processes actually work. A client can request for a service, right? Like the first part where a client, invokes, what we refer to as invocation. We can have remote invocation method. You are going to look at that. So this is like requesting for some kind of what? Maybe it could be a service or something. If the server doesn't have, it can invoke or actually talk to another server that has that particular resource. That's why you can say there's a server and there are two servers and actually client. So we can have this kind of back and forth kind of sharing of messages between the client and the server. The other system architecture that we need to understand as far as the distributed system is concerned is peer-to-peer. I think we understand this kind of arrangement where any kind of object or any kind of process within a distributed system perform equal task. So we don't really have a dedicated computer. One computer can work as a server, at the same time it can work as a client. So they perform in a peer manner. So we can't really have a situation whereby one is actually greater than that. So I hope you understand this, but we rarely have this. Specifically, it's implemented in the within the lower network level, like local area network, so that it's connected to the major client server system. So we are still going to look at the various architectures, I believe, in our next discussion. So this particular diagram shows how there's a back and forth. So every peer is actually communicating to the other one. There are other consequences or cons that comes on board when you implement this kind of architecture. Like you can say, there's no centralized way of managing the requests, from the client to the server, right? There's no control actually. So this one can cause a lot of delay and jam in as far as the process is communicating. Fine. Now, without understanding of the system architecture, now let's now break it down. Let's now understand why do we really need to have the essentials part of the distributed system, right? Talking about the architecture. Architecture, we have seen, comprises of different components of the what? Distributed system. But for us to design this particular distributed system, right, in a right way, so that we can isolate issues that comes on board, right? Like the delay of sending and receiving maybe a given service. We have failure issues. We understand that distributed system actually work in a very, we can say, in a very complicated environment. We have a lot of things. In a network environment, there could be issue with cables or communication links. We could have server not responding. So how then do we design an appropriate distributed system component? So we need to understand the various models. So the motivation actually, or the reason behind coming up with this system, these particular models, is the difficulties and threats that a particular distributed system can be able to do to encounter. I'll give an example. As you can see, there are kind of many components that are subjected to various workload. Like talking about the internet as a distributed system, there are a lot of maybe additional websites or pages that are accessed or added day in, day out. So how do we handle that? So we need to dissect that into a model, right? And this model is what we refer to as the architectural model, to understand the various architecture, or better still, the physical model, the fundamental building blocks of coming up with this kind of distributed system. We also have a distributed system that works under different platforms, what we refer to as heterogeneous. It could be different hardwares. So how do we pass and ensure that the different systems within a distributed system or component communicate effectively under this kind of environment. So that is what informs us maybe to have also the physical model. We also have the internal problems such as synchronization, yeah, of clocks. We are aware that we don't have a global clock for this particular distributed system due to latency issues, maybe communication challenge issues, yeah, which could lead to some kind of failures. So we need to design this distributed system to thwart this kind of problems. So in such kind of manner, we need some kind of failure model, yeah, so that at least to understand, should we have this issue, how then can we ensure that the distributed system function as required. And of course, we have some external threats that could always face our distributed system. It could be internal or external, yeah, but better still, we need to have a security model that ensures that we have the right security mechanism for us to be able to avoid this kind of distributed systems problems of security. All right, so we have the different system models. As I mentioned, we have the physical model, we have the fundamental models, we have the architectural model, yeah, borrowing from the architecture design that you have already looked at, right? So each and every model is there to ensure that we have the right design, yeah, so that in case of scalability issues, in case of transparency issues, we should be in a position to have a distributed system that doesn't really fall into these particular problems, yeah. That's why we say systems that are intended for use in real-world environments should be designed to function correctly, yeah, in the widest possible range of circumstances, right? So the first building block that we need to understand are the physical model. Now, physical model are basically the hardware and the software, yeah. So this is the first model that actually shows or tells the designer of how this particular distributed system is to work. Talk about the arrangements of the communication links, the hardware, the networks, and so on. Of course, we are going to look at the interaction model that help us understand how the various parts of the distributed system communicate. So let's look at the physical model, right? So before we look at that, maybe architectural model, as I've mentioned also, helps ensure that the different components work in tandem and together. So the computational aspect, yeah, ensuring that maybe how one particular design or system component should work effectively with the other one. Talking about different servers, yeah, passing different processes or resources between them and so on. Now, the main part of these particular models, which we really need to understand, are the basic components that we require to ensure that a particular distributed system functions are what we refer to as the fundamental models. I think I've already mentioned them. So we're going to look at the interaction model, how the different parts of the distributed system communicate, yeah. Also, we have failure model, right? Should we have issues with the link, yeah, maybe there's no reception of a particular process, right, or thread, how do we handle that? We also have security models that actually help us ensure that we protect any given distributed system against any external or internal interference. So we are aware of all this, it's only that maybe we don't know how to string them together. So when you talk about the first model, the physical model, as I've said, these are the foundation or the building blocks, yeah, of a particular distributed system. So we talk about the underlying hardware elements, right? And this particular hardware elements, as we know, they manage, or we have a lot of other physical components that are attached to these hardware elements, yeah. So the work here is to kind of bring or come up with some kind of abstraction layer so that other applications running on this particular hardware really don't have difficulties understanding how the architecture of this physical model is, or the comprising architecture of this physical model is built. Now, as I mentioned, these are the building blocks, and that's why we call it the baseline physical model. So the concept of designing a distributed system starts from understanding the required hardware and rather the software, and how at a minimal level how the connection happens, right? So that's what informs the reason as to why maybe we need to design a particular distributed system. Now, but we had challenges, or we need to understand where are we coming from with respect to this physical model. So we need to understand the generations, yeah, that the various distributed systems were designed as far as the physical model is concerned, because we can't really talk about the physical model without mentioning how it has already or changed with the time, right? So we have the early distributed system under the generation of distributed systems. These were implemented in the year between 1970s and 80s. So at this point, what informed the reason as to why we require the distributed system is actually the existence of local area network technology, not even the internet. Even if there were internet, there were very minimal connection, right? So the internet kind of network were implemented. At some point we had the token ring technology being implemented, right? So they could only connect a few nodes. Like you can see, it was between 10 to 100. Yeah, file transfer was not really that good. Yeah, so we had a little sharing of resources within the early distributed system. So we can say at this point the physical model was really not effective. The other category or the other generation is the internet scale distributed systems, which were informed by the emergence of what? Internet. Yeah, so it was implemented or started in the year 1990s in response to the dramatic growth of the internet. Yeah, so the capability or the features of the distributed systems were expanded based on the what? It's due to the emergence of the internet. So the resource sharing was improved. Yeah, you can see most organizations started a kind of attaching their systems to actually operate within the what? The internet. And that's why we talk about this generation of internet scale distributed system. The last generation, because we're talking about 3 generations, is the current generation, the contemporary distributed system. We talk about the mobile computing distributed system that actually facilitate this kind of physical model. So we have the mobile devices that can help us move from one location to the other, yeah, without really, it brings the openness characteristics of distributed system. It also provides, you remember we talked about transparency, location transparency, right? We also have ubiquitous computing, the wireless technology that allows the embedded of different objects. I mean, talking about the washing machine, yeah, these are things, they are computerized in a manner to ensure that we can have this kind of what? Distributed systems arrangement. We are aware or familiar with the computing or cloud computing, where we have different versions. We have cluster computing, we have grid computing. All these enables us to maybe interact with different services. We talk about platform as a service, so you really don't need to have physical platform. You also talk about software as a service, yeah, and name them, the different services that cloud computing offers. That what we can actually talk about a contemporary distributed system. So we can see the far we have come from, the far we have come from. Kindly. Now you either mute or I remove you from the meeting. It's simple. Yeah, we are all grown-ups, man. Don't interfere with our class. Perfect. So those are the generations of the distributed systems that we can actually talk about as far as the physical model is concerned. So in a nutshell, you can say the kind of features, or rather the characteristics that were adopted in the different generations. Yeah. So in the early distributed systems, actually the scalability was really not that large, it was small, and so on. So those are whatever we have already discussed. So this is what informed the arrangement or how the architecture of these distributed systems were modeled under the physical model. So I think that is very, very clear when you talk about the physical model. Now, the other model, which is really very, very important, and you have already looked at it, this is how the various components or the blueprint of the distributed systems are linked or tied together. So it allows us to have the separated or the specified components and understand their relationships. So it brings on board also for us to understand how communication happens between these different components. We have so far mentioned the various interfaces, right? So how then do you design a particular distributed system? Talking about architecture, yeah, it's like a house. Yeah, how do you design a house? Yeah, the good thing is that the distributed system or this model should give some room for future scalability, addition of other components and the interfaces, because if you add a component, there must also be a given interfaces. When I talk about interface, I think you recall the service interface and the rest of the interfaces that we have talked about, right? Now, the architecture model is boosted by the various elements, yeah, and we need to really ensure that we understand these particular elements, right? Someone is asking for Zoom link. Anyway, so we can understand the various building blocks of a distributed system under the architectural model by answering these four fundamental questions, right? When we talk about communication, we need to ask, what are the entities that are communicating in this kind of distributed system, right? What kind of entities? Is it client talking to a client? Is it server talking to server, and so on? After we have understood the entities that are communicating in a given distributed system, we then ask the following question: how do they communicate? Yeah. So the first question, we can pull out the communicating entities in a distributed system. The second question, how do they communicate? We pull out the communication paradigm in this particular system. So I think the first actually shows or make us understand how communication happens. The second two questions maybe help us understand how group communication happens. Yeah, what we refer to as indirect communications. Yeah, so we'll look at how the physical distributed structures are mapped, the roles and responsibilities of each and every object. Yeah, we are going to look at the client stub talking to the server stub, and the remote method invocation and the remote procedural call. Yeah, whereby we need to have the different roles and responsibilities. So let's look at how we can answer these two, or actually the questions. So the first two questions help us understand how to identify the various communicating entities. So we can solve these particular questions by looking at my friend, that's the last warning. All right, so we can have this question answered based on the system-oriented approach or problem-oriented approach. We have two categories of communicating entities. Yeah, we have the system-oriented entities and the problem-oriented entities. When we talk about the system-oriented entities, we look at how the various components communicate, yeah, by bringing in the idea of processes, right? So if a server and a client, for instance, communicate, there's some kind of processes that are initiated, yeah, and that's what informs the concept of inter-process communication. So we can have different processes being initiated from the client, yeah, and the server needs to actually respond or actually get to understand those particular processes. So that is from the system oriented. So processes is one of the things that helps these particular communicating entities achieve the objective. The other part of the system oriented option is to understand how the various nodes are integrated, and this is the concept we need to understand also again how we can improve the different processes, because if we have many nodes connected in a given distributed environment, we also need to boost and understand how we can manage the various processes. And speaking of managing or supplementing these activities of the processes, we are going to understand how to how the various processes use the threads to communicate. So we are going to look at inter-process communication in details. I think it's in our next class, and how the various threads within a process plays different roles. All right, from the programming perspective, for those who are good programmers, we need to understand how to program the various objects, so that they can communicate effectively with one another. As I mentioned, we have the components. We can also have the interfaces that provides these particular services, such as the web services and so on. So from the programming perspective, we can provide a problem-oriented approach. So here, the communication entities could be objects. And remember, an object or a message, an object is something that we really need to, for example, secure. We need to know how the various objects interact and so on, amongst or between the various components, right? So when we talk about the interaction and so on, we are going to look at the interaction model under the fundamental models. Now, after understanding the communicating entities, then how do they communicate? The concept of communication paradigms, right? So we have three categories of ways that this particular communicating entities uses. They can communicate via the processes, sharing of processes, in what we refer to as inter-process communication. They can invoke some kind of process remotely, in what we can look at as remote procedural call or remote invocation methods. We can also have some kind of group communication, which I refer to as indirect form of communication. I think the first two bullets, inter-process and remote, happen indirectly. So you must have two nodes communicating, right, at the same time. Not really at the same time, but they should be available. But in direct communication, the two nodes really, they don't need to be available, or they don't need to have some kind of time frame for communication. Okay, let's understand more about this. So as I mentioned, inter-process communication, there must be some kind of message or process that is shared, right? They can be shared amongst the different applications or objects for that matter, or better still, clients sending a message to a particular server, right? Remember the interfaces that can be provided by the application programming interface. Now, when I talk about the API, it reminds me of maybe the assignment that I gave you last time to understand the various internet protocols, and also the various what we refer to as the ports. So if you did that assignment, then you should be able to understand what sockets are. Because these are the interfaces that allows the two components within a distributed system to communicate. You can imagine the socket at home, the electricity socket. So when you plug in maybe some kind of interface, you must have the appropriate plug-in so that you use the right socket. So if you don't have the right protocol or port, then we can't communicate in this kind of inter-process communication. So it happens a lot in the one to point to multi-point communication, in what we refer to as multicast communication. Of course, this multicast communication also is going to inform us to understand how group communication happens, right? Remote invocation, as I mentioned, we can have different ways of invoking the server or the end node, yeah, the receiving node. So we can do that through different operations, procedures, yeah, or method. We are going to look at inter-process communication and look at all these invocation procedures in details. Like when we talk about maybe some kind of request, yeah, when you request for a particular web page, yeah, there's some kind of communication between the client request and also the web server response, yeah, in what we refer to as the request reply protocols, yeah. So again, I'll kindly request you to understand the various protocols that we have and also the ports, yeah. Also determine and understand the various secure ports, right, and those ones that are not secure. Of course, we have the remote procedural calls, which is more or less the same as the remote method invocation, yeah. But in remote method invocation, now we have objects, yeah, invoking some kind of request, right? So we are going to look at them in details, but again, understand that this is how the various entities communicate through remote invocation. I think the last part is the indirect communication that happens between the two entities, right? As I mentioned, the former options that you have looked at kind of gives direct communication, in that there must or there should be some kind of availability of the sending and the receiving node, yeah, communicating together, right? So in contrast, a number of techniques have emerged whereby communication is indirect through a third entity, allowing a strong degree of decoupling between senders and receivers. Decoupling means there's no need of knowing whether a sender and receiver is there, yeah, so you decouple the engagement, right? So in particular, senders do not need to know who they are sending to, what we refer to as space and coupling, and of course the time frame, yeah. Senders and receivers do not need to know the existence of them. So we normally say that we have the kind of message queues, yeah, where a sender can just queue the message at the receiving end, yeah. So they can always, or the end or the recipient can always read those particular message at some given time. It could be even after some months or years. So talking about indirect communication, we have different techniques, as I mentioned. One of them is the group communication. Now, a good example of group communication is a multicast form of communication, or even broadcast communication. I believe you guys know this concept, where a particular machine, if they want to communicate with other machines, they don't care who will receive that particular machine, but they need to have or become part of a particular network for this group communication to happen. So that's the concept, right? So we can have a communication where different processes are actually communicating, yeah, haphazardly within a group. So it doesn't really matter who is going to get that particular message, but for you to join the group, you must subscribe, yeah. So we can always have the concept of the different processes joining, yeah, or subscribing to some formation or group communication, so that they be part of that particular part of communication. So actually here there's some kind of identification that is given to the processes, right, so that at least some kind of when the distribution or actually the sending of this kind of messages can be monitored or tracked. As I mentioned, we can have message queues. Yeah, here is where maybe the sending computer, for that matter, sends it to the end computer, yeah, or the recipient, and queues that particular those particular messages, yeah. A common term is the buffer, yeah, creating some kind of buffer so that at least the receiving computer can always get to read those particular messages at some given time. Another concept is the tuple spaces. Now tuple, for those who are maybe good in database development, you understand that tuple refers to some kind of records, yeah, where you store some information, right? So tuple spaces here can refer to how this particular communication how they structure, how they store these particular messages, which can be read. Yeah, so if once they have been read from the tuple spaces, they can be deleted or removed, then brought, the other new messages are brought into the tuple space, and so on. So it's kind of a pipe or a way to manage the various messages. All this is courtesy of indirect communication. Remember, when we were talking about the shared memory, I said that we're going to meet it again. So indirect communication, this is a concept where the different processes have the ability to actually communicate or read or understand the different messages on different memory spaces, right? So the distributed shared memory, as you have seen, what we talked about, the tightly coupled way, right? So programmers have the ability to ensure that every computer or every process has some kind of memory, and there is some kind of layer, as you had seen, yeah, that ensures that different computers, different processes can be able to read the memory addresses, yeah, without any given challenges. So the concept here, or the major obstacle so that this kind of communication happens effectively, is the ability of some kind of copy of messages to be replicated within this kind of arrangement, so that each and every process can be able to read the message in a synchronized manner and providing some consistency. Otherwise, it's going to create some kind of challenges that you're going to look at just in a few. So those are the kind of communication. We had the communication paradigms, how these particular entities communicate, and of course we had the communicating entities, what is communicating, right? So we mentioned the various entities. We had the problem-oriented option, the system-oriented option. We have also looked at the interprocess communication through message passing, multicast, and so on, up to the last option, which we had indirect communication. Perfect. So to wrap up the idea of architecture model, we have the patterns. Patterns actually are there to supplement the elements that we have already looked at, how the communication happens, right? So when we talk about the patterns, we can always categorize, or what we refer to as actually separating the various communication patterns. Yeah, we can have communication in different layers, right? Like, I'll take you back to how OSI model is implemented, yeah, within a network. OSI model operates under 7 layers. So each and every layer kind of communicates with a different, or the layer above or below it. So the same concept. We can have architectural patterns having the different layering options. So here we have already looked at operating system. So you can layer the communication that happens within the applications. We can have middleware, and of course the concept of abstraction comes in, so that at least whatever is operating within the upper layer doesn't really bother to understand what is happening within the lower layer. So these are some of the layers that complements the kind of elements or architectural elements that you have already looked at. Why do we need layers? To actually facilitate transparent communication, to create some kind of fault tolerance way, so that you can really isolate, yeah, the layers that really are not actually operating. Now, to further understand this layering, we can again categorize the various layers into what we refer to as tiers, yeah, or what we commonly refer to as the tiered architecture. We understand the concept of 1 tier, 2 tier, 3 tier architecture in the networking field, yeah, where a client communicates with a server. That is one. That is Okay, sorry for that. Let me connect again. I hope that is the first time that this is bringing issues. So I believe we understand that concept of the tiering, in particular with respect to the network, yeah, where we have one tier, we have two tier, three tier, based on the kind of communication that is happening between the client and the server. And of course, if you have some kind of storage facility, we can also have the third tier contacting the database. So that's what we refer to as the tiering, yeah, organizing some kind of functionality into understandable manner. So the concept of two and three tiered, as I mentioned, we have the three approaches. How the user interact with the applications. Yeah, again, I'll refer you to the OSI model, how the presentation layer, right? So the various applications, yeah, can also inform how we can actually pick or store data within the given databases, right? So we have this concept that we need to understand when we talk about 2-3 tiered architecture. The first approach is to use or have the presentation logic, allows the users to interact with the application. Yeah, the application logic provides an environment that various applications can run or communicate. Within an organization, we can talk about various applications, yeah, like the business application that comprises of finance, maybe applications, HR applications. Where do we store this data? So we need to engage the other tier, which is the third tier, data logic. Yeah, so it's concerned with how we store or actually interrogate data within the database through the concept of data management system. So there's a diagram here showing how the two-tier architecture is actually implemented. You can see we have the client machines, or the client computer, showing some kind of user controls, user views. Yeah, so there's a direct communication between the client computers and the server computers. We can also have the client applications or the server applications actually responding. So that's the two-tier approach, very familiar. We have the third tier, that is bring the data logic, yeah, the database into perspective. Yeah. Like you are seated behind your machine using or requesting for a particular web page, yeah. So that web page, you interact with the web browser, it brings the interface, the form, yeah, you populate the form, you store the data within the database manager. So I think that is a three-tier architecture that also we need to understand when talking about this kind of architectural model. So try to understand the OSI layer model. I think it's going to play a major role when you are going to be talking about networking of these various distributed systems. Now, the final model, and which is a very, very important model when it comes to designing the essential components of a distributed system, right? So here it's like dissecting into the nitty-gritties the main problem that can face this particular distributed system, as you have seen. So how do we then have some kind of models or fundamentals, as the name suggests, so that we provide the right design for the various categories or components that we have already seen. So we are going to look at the various categories of fundamental models. As you can see, in general, a fundamental model should contain only the essential ingredients that we need to consider in order to understand and reason about some aspects of systems behavior. So it just offers some very common and actually essential components that we need to understand. So talking about the fundamental models, we have different categories. We have so far seen the interaction, how the various components communicate between themselves. So they interact. We are going to look at interprocess communication, which happens asynchronously and synchronously. right? So there are those interaction that happens amongst the different components synchronously and asynchronously. We have failure, and this is the model that allows us to design a particular distributed system so that it can handle the various failures that we can realize in what we refer to as fault tolerance mechanism. We are going to look at some kind of failures that are likely to be achieved. Like we can have the channel issues where the actually communication happens, and so on. And most importantly, the security model. Yeah, this ensures that we can actually design a particular distributed system so that it doesn't really have issues of security. Perfect. So when we talk about interaction model, so this is one of the fundamental models that we have already looked at. So the key issues here, or the significant factors here that affects this kind of model, okay, sorry for that once again. So let me just share the screen again. So as I mentioned, one of the fundamental models is the interaction model, that we need to understand the two significant roles that is playing. We need to look at the communication performance, right? When we have two components of a distributed system and how communication happens. How is the performance? Because that is very, very essential. Yeah. The other one is the aspect of delay, yeah, or the ability of sending what we refer to as latency, because we don't have a global clock. Yeah. So how do we maybe have or achieve this? Yeah. So it is impossible to maintain a single global notion of time. So then how do we deal with that kind of concept? So that is the interaction model, right? So performance of communication channels, yeah, can be attributed to three factors relating to latency. I've already mentioned that. Now we can have different approaches to latency. Yeah, of course, when you look at transmission of messages, yeah, it's the time. Yeah, so people can say it's the time from where a particular sending process released the message to the time the recipient maybe read that particular message. Yeah, or we can give other versions of latency. Any other version that can describe what latency is? I can get we can have some feedback. Some ways that you can also describe latency, using an example very fast. Yes. Oguta.
An example of a latency is whereby when a person transmits a message over the network, it reaches at an unexpected time rather than the expected one.
So that is the network. Any other latency example? I know we have different examples that we can give when we talk about latency. Anyway, with respect to the communicating entities, this is very, very vital. Yeah, and we need to take note of this. Yeah. So the bandwidth also is something. Is another factor to be considered when designing a particular distributed system. Right. So, of course, this is a network term, right? That maybe ensures that you have the enough or the capability to transmit some kind of information at a given time. We have jitters that is really noted when transmitting some kind of multimedia data. I've given an example here like if consecutive samples of audio data are played with different time intervals, the sound will be badly distorted. So I think these are some of the faces that the problems that we are actually facing even right now. Yeah, all this applies to what we are doing now. Yeah, and I think they, in one way, hinders the right performance of communication within the distributed system. So take note of that. We also have, and I think maybe I'll request someone to read for us the computer clocks and timing events with respect to the performance. So any volunteer to read for us this under computer clocks and timing events? Kellen? Or who is that?
Christine.
Yeah, Christine, can go ahead.
Each computer in a distributed system has its own internal clock, which can be used by local process to obtain the value of the current time. Therefore,
Is it
may supply different time values. This is because computer clocks drift from perfect time, and more importantly, their drift rates differ from one another. The term clock drift rate refers to the rate at which a computer clock deviates from a perfect reference clock.
all right? Thanks. I don't know whether the challenge is from my side, but I could hardly hear you. I hope you're not experiencing the same from my side. So this is just brought in this kind of content here just to illustrate the fact that we don't have one common global clock for the communicating entities, because you can see the issues here. Distributed system have their own internal clock, and most importantly, for example, when a message is on transit, yeah, for example, when you're requesting some service from a server, yeah, it could happen that maybe there's some kind of delay or in network connection, yeah, and better still, maybe the bandwidth issue also could play the role. That's why we can't really say. You can tell someone can tell you, but I sent the message 20 minutes ago, yeah, but on your side you'll say I haven't seen the message, yeah. So there could be issues. So there could be issues in between the communicating or the communication channels, apart from maybe the computers themselves. So those are some of the things that we need to put into consideration. The other aspect is the variance when it comes to the interaction, yeah, the interaction model, right? Because we have seen that there are two processes, or there are communication between two nodes within a distributed system, right? So there are factors that you need to put into consideration: how the message is being passed from the sending process maybe to the receiving process. So this can happen in two ways, right? Either synchronously or asynchronously, as I'd already mentioned. Maybe the difference here, as when you're going to be looking at the inter-process communication, I'm going to maybe describe this one in details. Here we can tell or refer to the synchronous distributed as kind of communication that has some kind of time bound. They are time bound, so we can always have the lowest time frame or the highest time frame, or in between some kind of timing. Whereas the asynchronous really doesn't care, yeah, even if it gets to the recipient after some several days or maybe months. In a nutshell, we talk about synchronous distributed system as using the acknowledgement, what we refer to as a transmission control protocol. For the synchronous distributed system, they tend to use a datagram control protocol. So one acknowledges the recipient, or actually has a way of managing the message that is being transmitted. The other one doesn't have that capability. So those are the two variants, and I think there's a quiz within the exercise. I've asked a particular question about these variants, so I believe you can successfully answer that. Now, the failure model is, I think, also the other model that allows us to understand how we can design the various distributed systems so that they can be able to handle this kind of failure. So I'll really brush very fast. So we have the omission failures. Omission failures is part of the failure model, talking about process omission failures. So here is with respect to maybe if, for example, the channel is overloaded or the system is not able to handle the given process, then the process crashes. So we say that is a process omission failure. Also, we have communication omission failure, where there's some part of messages that are really not sent to the receiving process or computer. So chances are the receiving computer will not get the entire message. It could be due to communication link or just some kind of disorganization when the message is being transported. So take note of the two omission failures. The other category are arbitrary failures. Arbitrary failures are things that really don't have reason as to why they happen. For example, a process may set wrong values in its data items, or it may return a wrong value in response to an invocation. So here there's no really, the values that are given is not actually the values that are received, maybe because of distortion of the message, corruption of the message, or maybe hacking. Like when the message, we have the mobile code, we are going to look at the security model. Someone can tap into that and maybe change or alter how the message looks like, so we don't deliver the real message. That is arbitrary failures. So you can say the various failures, omission, crash, arbitrary, and failure, and the description. So some happens or affects the channel, the communication channel, but you can say majorly they affect the process. So omission actually happens within the channel. The last and the final model is the security model. Now, talking about the very many fundamental models that you have looked at. We have looked at the interaction fundamental model. We have also looked at the which model is this? We have also looked at the failure, and also the security model. There are very many models. Sometimes it can confuse you. So the security model allows us to, as it suggests, it can be achieved by securing the process and the channels. Because we have seen from these particular failures, we can have issues with the process and also the channel. So it's very, very important that we can be able to, that we should be able to secure these kind of options. Now, we can see a client there, or the principal user, trying maybe to access some objects on a server. This object could be maybe a database object or a confidential file for that matter, right? So it's, there's some kind of invocation. So how do we thwart, or how do we reinforce security? So we can provide the user with the right access, rights, so privileges, so that they can access just only the part of the object that they need to access. So that's how we actually determine how to design the security model of the distributed system. Again, you can say the problem that we are likely to have when you have some kind of attack. So when a particular user or a processor are communicating via the communication channel, we can have some hacker or someone tapping and having a copy of the original message. They can what we refer to as they can change or alter that particular message, then release it so that it's being sent as a different message altogether. So I believe we understand the security paradigm. Here we talk about integrity of the data being compromised, or the integrity of the message being compromised. So that is some of the issues that you're likely to get when actually using or having this particular model. So how do we then defeat these security threats or challenges that we get? So we have the concept of cryptography, where we have the encryption mechanism, providing some keys, right, where the sender and the receiving processes are the only ones who can be able to decrypt a particular message. So that's one way. Authentication happens in different levels. So based on the key, it's only the person or the process that has the right key or the right encryption key are the ones who are allowed to access that. That's what we refer to as being authenticated. And of course, we have different ways of securing a channel. A good example is where we transmit data via the network using virtual private networks, or what we have referred to as the VPNs. So when we are building or designing these distributed systems, we need to put into consideration this aspect of securing the various channels. So ladies and gentlemen, I think we have brushed through the concept of distributed system architectures, and also understanding how these particular architectures are implemented using the various models. So you should be in a position to identify first the various building blocks of these architectures. Talking about the distributed system hardwares, talking about the distributed system softwares, right? Those, the middleware, network operating system, and so on. Of course, you're going to look at the various softwares at some point. Again, you need to be able to identify the various challenges, how the various challenges can be addressed using the models that you have already mentioned. So you can talk about the bigger model, architectural model, right? We have also looked at the fundamental model, and of course the fundamental model has a lot of other models such as a security model, and of course we looked at also the physical model that comprised of different what we refer to as the different generations. So I think I'll stop there, unless if you have a question, if